on from our exponential recap. We looked at the making powers table and the index laws in the previous video. In this video, we're just going to be looking at how using algebra and using index laws and solving for these exponential functions in many different settings. So let's get started. The first thing we're going to look at is we're going to be, let's just go back to my notes. Here we go. We're just going to be doing some evaluating first. So I'll write that in. Exponentials. Okay, so let's start off with a few examples here. First one, you're asked to evaluate the following. So we have 64 to the power of 3 on 2, and the next one is going to be 32 to the power of negative 2 on 3. So I'm just going straight into these kinds of ones. Firstly, just the ones I always find the hardest, so we're going to get into this. First step with this one is I like to break this one up and write it in this form. Okay, so 64 to the half or to the power of 3. The next thing is that we know that this will convert into a square root, all cubed, 4 cubed, and we know the answer is 64. Now you can go about this the other way, where you can go 64 cubed to the power of a half, right? Now, do you know what 64 cubed is? I'm not sure if you do, but this way is going to be definitely more challenging. So what I recommend doing is deal with that fraction first, and then because the number goes smaller, and then you cube it or square it, whatever, to make it go bigger. So this way is a lot harder, so that's why I'd recommend doing the fraction first. Okay, for B, we're going to do the same thing. So here we go. I'm going to go 32. I think that was meant to be a 5. That's going to be quite hard to do otherwise. So 32 to the 1/5, and then I get the negative 2 outside. Now I know that 2 to the power of 5 makes 32 there. We can express this, if you like, in terms of this form. I don't often do that anymore, but so something to the power of 5 makes 32. Well, we know the answer there would have to be 2, right? So if we look at the table up here, you can always go back to that. 2 to the power of 5 is 32. Okay, so we need to know these numbers pretty well. 2 to the negative 2. This becomes 1 on 2 squared. We can keep going. 1 on 4 is our final answer. Okay, so this is how we tackle these problems. We've used negative indices here and fractional indices. We're going to move on with our evaluating exponentials, and we're going to move on with looking at exponential expressions, so simplifying exponential expressions. Don't know why I wrote it that way around. There we go. So here we go. We're going to get into this, and I'll scroll down, and let's write out a few examples. So the first ones I have are going to be, and I think it was, I should know this one. I just have to make one up on the spot here. X to the half. We're going to expand this and simplify. So x 3 on 2, take 2x, let's put a 2 there. Let's make that 3. So I am going to simplify this function here. So we can crab claw it, and now it's going to come 2 to the power of x of a half plus 3 on 2, our first index rule. So half plus 3 on 2 becomes 4 on 2. And then we've got take 4 lots of x 3 plus a half. This is going to be 2x squared, and then 3 plus a half, well, that's going to become 6 on 2, so 7 on 2. like that. Now you can, if you want, express this as x to the 7 if you so wish. You don't need to, but yeah. This is us expanding and then simplifying, collecting the indices. Some other problems that typically people find hard are ones that look like this. Okay, so here we go. First step, we're asked to simplify this first one here. Now, common strategy here is we need to get everything out of the same base. We can see that this is 3, but this is 6. So we can re-express this as 3 to the n plus 3 times 2 all to the n on 3 to the n. Okay, this may seem unusual, but what's a really handy strategy here is expanding all of our powers. Okay, so getting into this base form is really handy. Now we can see that there's a 3 to the n that's common in the top, the numerator, and a 3 to the n at the bottom. So we can factorize the 3 to the n out. What's left over? On 3 to the n. Now this is useful since we have a multiplier here, 3 on 3 on n. We can cancel them out and we're left with 1 plus 2 to the n. Okay. On the right hand side, we're going to do the same thing. Now you can see here, this n plus 2, break it apart. I really want it to look like this. It just becomes so much clearer what we're doing when we get rid of those indices. Now I can see that common factor of 2 to the n on the top. I'm left with 2 squared minus 1 on 2 to the n. We can cross out the 2 to the n's, and I'm left with 4 minus 1, that's 2 squared, which is 3. Last one, to do exactly the same thing here. Over 9. Just keep going with the same strategy. 2 to the n on 2 cubed plus 1 on 9. And then we can evaluate 2 cubed plus 1 is 9 over 9. The answer is 2 to the n. And we look at this expression up there and go, oh yeah, of course it's 2 to the n. It's pretty amazing what these index rules can do if you know them well. Now, the reason I've shown you these ones is I'm finding that from experience, these ones are students find difficult. We're going to go into some factorizing now, so we can also apply some quadratics here. We're also going to get into something called a dummy variable, and I'll show you how to use one. That's dummy variable helps you simplify some problems. So we're going to keep going with these problems here. We're asked to factorize, and in this case it's exponentials. Okay. So here we go, the examples I have. 4 to the x take 9, and the other one is 9x plus 4, 3 to the x plus 4. And then I've got 2 to the n plus 3 plus 8. Now we're going to look at something called the dummy variable to start off with, but we can see that this is 4 to the x take 9, and we want to factorize this. So first thing is what we can do is we can go, okay, we can express 4 as base 2. Like that. So it's going to be 2 squared to the x take 9. The next thing we're going to do is go 2 to the 2x minus 9. And then we go, okay, we're going to use a dummy variable here. So we can say, let y equal 2 to the x. Okay, now let's see if this is going to come in handy. There's going to be 2 to the x squared minus 9. So we see here, if I expand this, it's going to make 2 to the x. The reason I've done this is now I can sub in my y value. So let's replace the dummy. It's going to be y squared minus 9. And then we recognize this as a difference of perfect squares. And the rule for getting factorizing these is you take a square root of both of these and make 1 plus and 1 minus. The square root of y squared is going to be y. So here we go. We've got y. Square root of 9 is going to be 3. We make two brackets like this. 1's plus, 1's minus. So if I expand this, we can see it's going to be y squared, and then the 3y and the negative 3y cancel, so the y term's gone, and then positive 3 times negative 3 is negative 9. Thing is, we've got to swap the dummy variable back out. So that dummy variable has helped us factorize. It's far clearer seeing it than from there. And then we can go, okay, this is going to be 2 to the x plus 3, brackets 2 to the x, take 3. Now, if I want to check if this works, I can use the old crab claw and see if it makes that 4x take 9. Let's have a look. 2 to the x times 2 to the x is indeed 4 to the x. And then I've got the plus 3 times 2 to the x, take 3 times 2 to the x, take 9. They cancel, and we can see we're left with the same expression at the top. This is called a difference of perfect squares. It can be hard to see. Rule of thumb, make this a squared term, and you see how there's no the power of x term there. So this is sort of, you just need to recognize it. We're going to move on to this one over here actually first, and then we'll move on to this one. In this case here, we are asked to factorize. Now, with this one, what we're going to do is we're going to expand this n plus 3. Okay, so this is going to be 2 to the n times by 2 to the 3. We're reverse engineering the index rule, the first index rule. If you work backwards, it makes this. Now, it's very, very good in these examples to have a common base. So 8 can be expressed as 2 cubed. Remember that table, we should recognize 8 as 2 cubed. Now that we can do that, we can factorize out the 2 cubed. And then we can go 2 cubed is 8. So it's 8 lots of 2n plus 1. Now this is in factorized form, so we've done that one there. The last one is this one over here. Now there's a trick with this one, it's very similar to this, is we need to recognize that there's a common base of 3 to the x and 9 to the x. When you have this kind of expression like this, we're going to be expecting this to be a, a quadratic. Okay, so first step is I know this is going to be 3 to the 2x plus 4 times 3 to the x plus 4, like that. Now you can have a look into why that's the case. 9 to the x is equal to 3 to the 2x, but when you've done enough of these, you can go straight there. Now we can use our dummy if you so wish. Okay, we can go let y equal 3 to the x, and then we can swap in y squared plus 4y plus 4. And now we can factorize this pretty easily. It's from the quadratics part of the A and ASL course. So it's going to be y plus 2, which can be expressed as y plus 2 all squared. And then we just have to sub that dummy back in. So it's going to be 3 to the x plus 2 all squared. And that there is a factorized form of this part up, this question up here. Okay, so just one step is the dummy. Just make sure you sub out the dummy. The last step. It's just sort of, it's like a placeholder variable that makes maths a bit easier. We're not used to seeing 3 to the x so much and 3 to the 2x, but we can see y squared. It just becomes easier to see these quadratics. Now you're welcome to factorize these without a dummy. If you can see this to this, that's fine, you know, like if you can go straight there, that's great. It means you've done lots of these. All right, now we've factorized exponentials, and you know, there's plenty more examples out there, but we're going to move on and we're going to look at solving exponential functions, okay? So let's scroll down here and get into some solving. Okay. Solving. Okay, the first examples we're going to look at, 2x take 2 is equal to 1 on 64. 27, 3 to the x is equal to 9 to the power of 2x plus 4. And then e to the x plus 1 is equal to 1 on the cube root of e. Now, I have made up these examples, so you may find that they're not the best. The numbers might not be super nice, but you know that in a test, they're going to be a bit nicer here. So, okay, I'm just waiting for this to sync. There we go. It's all loading up now. Great. Now, with all these, I'd recommend the first step. You want to get the bases the same. No coefficients. Okay. So this is your first aim typically when solving exponentials. So are the bases the same and are there no coefficients to the powers? What I mean by no coefficients is it should just be like 3 to the something is equal to 3 to the something. I don't want to see a 2 times 3 to the something is equal to 3 times 3 to the something. It's not going to work that way. We need to get the coefficients away and just have the bases by themselves. So over here we can see we've got 2 to the power of x take 2 is equal to 1 and 64. Can we make the bases the same? Yes, we know that 2 to the power of what? 6 is going to be 64. So let's do that. Next step is let's bring this up to the numerator. Like that. Now we can see, so I'm trying to simplify all this and express as one single base. We've got the same bases. We've done the first step, there's no coefficients. That's good. The next step is we solve the indices. Okay, so we actually make an expression out of it. So if the bases are the same and there's only one thing on the left-hand side and the right-hand side, it stands to reason that x take 2 must be equal to -6. So x take 2 is equal to -6, so x must be -4. And there's our answer. X is equal to -4. And my internet's just getting a little buggy here, so hopefully you'll see it coming up soon. And I'll see if I can sync it as well, just to tell it to, get with the program. The next one I'm going to do is 27 to the 3x is equal to 9 to the power of 2x plus 2 plus 4. And in this example, it's not as straightforward as this one. This is already to the power of 2, and this just, you match it up. This one, we need to find a common power for both 27 and 9. We know from the table from the last video that 3 to the power of 3 makes 27, 3 to the power of 2 makes 9. So we can re-express this like so. 3 to the power of 3, 3x, is equal to 3 to the power of 2, 2x plus 4. Now we need to simplify this and express this as a single index. So 3 to the power of 9x is equal to 3 to the power of 4x plus 8. Now the answer here may be horrible, doesn't matter. We're now going to equate the indices here and here. 9x is equal to 4x plus 8. Take 4x from both sides. So 5x is equal to 8. Divide both sides by 5. 8 on 5. There's our answer. Now over here we have the e function. It's a natural exponential function. And it's just a special kind of power. It's in between 2 and 3. And it sort of comes about representing a continuous growth. It's just a number that's just a special number that just comes out of continuous growth. And each of the ones approximately, I think it's 2.718 or something like that. And it just gets continued because it's irrational. Okay, I hope that's correct there. I always forget that one. So first thing over here, we just treat it exactly the same. We want to express as a single base. Over here it's e. Over here there's an e hidden down here, which we want to bring up to the numerator. So let's have a crack at the right-hand side. Oh, let's change that to green. E to the x plus 1 is equal to, and I'm going to express this as e to a third. Now from my experience, I usually bring this all up at one step, but from my experience, we should do this in multiple steps because I think it's just picturing where this is going to go. Usually breaking up into multiple steps stops those errors. E to the negative third. and then we equate the indices. So there we go. Oh, my bad. We're going to take one from both sides. One of the most common errors I used to do at school as well. Keep doing it. There we go, -4 and 3. So I hope this was useful for solving exponentials. Obviously, if you can think of an extension of an idea, we could be asked to solve these. You know, like these factorizings up here. You could just whack an equals 0 on the end, and you need to solve both of these when this is equal to 0. An interesting problem which we will extend now because I think it is valuable to look at. So if I put an equals 0 on this, so in red I'll just continue this, we're going, okay, when is 3x plus 2 equal to 0? Well, we can rearrange -2, and we actually have to have a bit of a knowledge of the exponential function. I know that 3 to the x is going to look like this, and that it exists for y is greater than 0. Therefore, there is no solutions because we're trying to find when y is -2 and there's no intersection with the graph. So no solutions in this case. So we could be asked using this knowledge to go find the values of x. And this comes up a lot more in logarithms, and this is a bit later on. Okay, so what we've done now is we've solved exponentials and applied it to also basically our quadratic knowledge, so a bit of prior knowledge there. And I'm just going to show you 2 more examples of solving because they can come up, and yeah, from my experience, they sometimes are done well, but recap isn't going to hurt. And this will be the last 2 examples. So we've got 5 times 2 to the x is equal to 320. I'll change the colors there so we don't get confused. And the next one is going to be 2 times 1/3 the power of x. I've got take 2 there. Take 2 is equal to 162. Okay, now let's go back up to our steps again. We're going to get the bases the same and no coefficients. Now over here we didn't really have the coefficient issue, but we do over here. We've got a 5 in the front there, 2 over in the front here. So our first step is to get rid of those coefficients by dividing both sides by, in this case, 5. So we're going to go 2x is equal to. Now over here, I'm going to go, okay, well, what's 320 divided by 5? What you can do is divide by 10 and times by 2, or you can divide by 5 using your division. So how many times does 5 go into 32? 6, and we're going to carry the 2, so 64. There we go. Now, this is looking more familiar. 2 to the x is equal to, same bases, 2 to the power of, what's 64 again? Well, we should know it's 6. Therefore, equate the indices, x must be 6. Last example over here. May look a little scarier, but the same principle. We want to get rid of this coefficient of the power. So this is the same base to 1 and 3. So let's divide both sides by 2. And I'll change the blue here. You don't have to wrap a brackets around it, but it makes it look a little nicer. Then we need to go 162 divided by 2, which is 81. Now, we can see this is 1 on 3. Let's make that a numerator. 3 to the -1. X minus 2, and this is 3 to the power of 4. We know that from our table. Next step is let's get a single index there. -x plus 2 is equal to 3 to the 4, and now we can equate the powers. -x plus 2 is equal to 4, and then we can go -2, so 4. It depends which way around. In fact, I would probably do it this way. I should do it the way I would do it. Like that. I know sometimes if you're swapping it around too much, it can be a little bit hard on the head. So x is equal to -2 in that case. Now, this is the video we've done on basically using algebra for exponential functions. You can see how much knowledge it requires of our index laws and using our tables, and also factorizing, expanding, binomial expansion, difference of perfect squares, factorizing monic, quadratics. There is so much stuff in here, and yeah, if you don't have all that prior, this is going to be, yeah, it's usually a bit tricky, and that's why we do heaps of examples to practice, because there's a lot going on here. I hope this video is helpful for you. In the next video, we'll be looking at the exponential functions. Cheers.